Hello everyone, it's my great honor to introduce our work, Efficient Personalized Method by Click Search on ICDE 2022. My name is Kai Wang. I'm the first author of this work and I'm the presenter of today's topic. Here is the outline of today's presentation. Firstly, I will introduce the background knowledge and the problem definition, and then I will introduce the solutions from the baseline approach to the advanced approaches, and followed by the experiments and the conclusion. So the first part is the introduction. Bipartite graph serves as a very useful data model when modeling relationships between two different types of entities. For example, user moving networks, people location networks, and customer product networks. So the formal definition of bipartite graph, it is a graph whose vertices can be divided into two disjoint vertex layers, U and L, and every link, or say every edge, connects to a vertex in U to one in L. That is, U and L are independent sets. We can see the example graph as follows. It contains two different vertex layers, the upper layer U and the lower layer L, and the edges only exist between the two vertex layers. Cohesive subgraph is a very useful structure on bipartite graphs. It is subgraphs where the vertices are densely connected inside according to specific cohesive constructs. Well-known examples of cohesive subgraphs on bipartite graphs including alphabetical, k-by-tross, and Biclique. And the Biclique is defined as a complete bipartite subgraphs, which is for each pair of vertices U and V, there exists an edge UV in the Biclique. And for example, in this figure, it is a 3 times 2 Biclique because there are 3 upper vertices and 2 lower vertices, and the edges exist between each pair of vertices. So based on the Biclique model, the maximum Biclique search problem is studied in the literature, which is given a bipartite graph G, a pair of positive integer tau u and tau v. The problem of maximum Biclique search aims to find the Biclique C star such that it has at least tau u upper vertices and tau v lower vertices, and the size of the C star is maximized. Here we see the size is maximized. We refer to the number of edges is maximized in the Biclique. Below is the examples. Here is given a bipartite graph G, and given query parameter tau u equal to 1 and tau v equal to 1, we will return the maximum Biclique with 8 vertices. And if given tau u equal to 1 and tau v equal to 5, we will return the Biclique with 2 upper vertices and 6 lower vertices. The problem of maximum Biclique search is driven by many real-world applications. One representative one is detecting from clicking actions, or say detecting the anomaly groups. So in Alibaba company, there's a very common scenario for the from clicking actions. So step 1, the agent taking orders. The Taobao merchants have some fake order requests, and the agent will assign fake ordering to the high clients. And step 2, the high clients will make fake ordering. They will order and leave good reviews, and the Taobao merchant will send empty packages. And step 3, the high clients will give the proof of the good review, and the Taobao merchant will pay for the clients. So these fake buyers and products to promote will inclined to form a cohesive subgraph or to form a biclique because the fake buyers will commonly buy buy the same products in a same shop. So in the scenarios of Alibaba, the challenges is their balance of buyers of products and their more than 10 plus balance of transactions. So using the efficient Mason Biclique search approach on bipartite graph will significantly increase the recall and as they tested in the Double 11 Festival in 2017. And this paper is also published in RealDB 2020 and won the Best Paper Runner-Up award. So the Mason Biclique search only finds the biclique with the globally maximum size, but in many scenarios, the fraud detection techniques require a query seed, which is a confirmed risky account as the input. So from the seed, we can just obtain the fraud group. For example, in 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 this example, this vertex is a query seed, so we can get the maximum biclique containing this query vertex to get a personalized maximum biclique. Here is the definition of our personalized maximum biclique search problem. Given a bipartite graph G, a query vertex Q, and a pair of integer, so the problem is to find the biclique containing Q such that it has at least tau u upper vertices and tau v lower vertices, and the size of the maximum personalized maximum biclique is maximized. Here is an example. So given a bipartite graph G, so the personalized maximum biclique with Q equal to U1, tau equal to 1, tau L equal to 1 is the subgraph formed by 4 upper vertices and 3 lower vertices. So there are in total 12 edges. And if given the query parameter Q equal to U7, we will get the personalized maximum biclique which has only 9 edges. Now we will introduce the solutions for solving the personalized maximum biclique problem. So firstly, I will introduce the online computation approach. So the maximum biclique search problem is NP hard, and the personalized maximum biclique search problem is also NP hard. And the biclique search problems usually follows a branch and bound framework, including the maximal biclique enumeration and maximum biclique search. So using this branch and bound paradigm, they always to prune the non-maximal bicliques and preserve the maximal bicliques and return the one with the maximum size. Based on the branch and bound paradigm, the online algorithm for personalized maximum biclique search can be designed as follows. So we can first shrink the search space according to the query vertex, and then we can apply the state-of-the-art maximum biclique search algorithm in RealDB 2020. This idea is based on the definition of two-hop subgraph. Given a bipartite graph G and a query vertex, the two-hop subgraph of this query vertex is the subgraph induced by the one-hop and two-hop neighbors of this query vertex. And we have this lemma. So given a bipartite graph G, finding the personalized maximum biclique in G is equal to finding the maximum biclique in HQ. HQ is the two-hop subgraph of Q. Following this example, if we want to find the personalized maximum biclique of U7, Firstly, we can find the HQ of U7, which contains the vertices U1, U2, U4, and U5 to U7, and V4 to V6. And then in this subgraph, we run the Mason-Biclique search algorithm, and we will find the Mason-Biclique is containing these 6 vertices. Although the online algorithm can be finished in reasonable time in many cases, this totally online computation approach cannot satisfy the real-time requirements in many scenarios, so we resort to index-based solutions to solve this problem. And a naive index can be built as follows. We can just enumerating all the Q tau combinations and obtaining all the personalized Mason Bicliques using the online approaches. But this index is impractical since for a query vertex Q, the valid tau u and tau l values can be very large. So in total, we will have a very large number of personalized Mason Bicliques, which is hard to store and hard to retrieve. So the challenge is to design a reasonable index is as follows. Firstly, we need to design a size-bounded index which allows for both efficient construction and query processing. The challenge 2 is how to further reduce the indexing time with some cost sharing and optimization techniques. So here we introduce the PMBC index, which is based on the insights. Given a query vertex Q, each personalized Mason Biclique of Q can be the result of multiple Q tau u tau l combinations. So by identifying the coverage scope of each personalized Mason Biclique, we can build the index by only considering these critical combinations. For example, given a bipartite graph G, so this Biclique is the result of Q equal to U1, tau equal to 1, and tau L equal to 1. But it is also the result of Q equal to U1, tau U equal to 2, and tau U equal to 2. And so this one result can be the result of many combinations. So we only need to store the critical Bicliques. So the PMBC index consists of 2 parts. The first part is the forest T, which contains a set of search trees. The second part is the array A, which contains a set of personalized Mason Bicliques. And here is the example of the search tree Tu1 of U1 and a part of the array A. We can see in each tree node, it firstly contains a pair of parameters, which is tau u and tau l. So the first tau u and tau l is 1, 1. It will refer to a 4 times 3 Biclique, which is C1. And the Biclique is actually stored in the array A. And then in the second level, it will contains 2 sets of parameters, 1, 4 and 5, 1. These two will refer to two Bicliques, C2 and C3, which are stored in the array A. So the rationale of the PMBC index is shown in this figure. When we query the U1, tau u equal to 1, tau l equal to 1, the result C1 will cover this search space, which means that given any parameters tau u equal to 2, tau u equal to 3, tau l equal to 2 to 3, so if the query parameter is contained in this rectangle, tau C1 is the result. So only if we query 1, 4, we will have another result, which is C2. So C2 will cover this rectangle as the result. And then if we query 1, 5, we will have another result, C4. So C4 will cover this search space. So we can only store 4 Bicliques to cover the search space of query vertex U1. The query process based on the PMBC index is also very simple. We can firstly obtain the, for example, given parameters U1 to 4. Firstly, we obtain the root node and verify the size of the Biclique stored in the node. And because the size constraint is not satisfied, C1 cannot be the result. Then we check the children node of the root node, and we find that C2 is a 2 times 4 Biclique. We satisfy the query constraint, and we return C2 as the result. And the query time is also well bounded. So the main framework to construct the PMBC index is to build the search tree for each vertex Q, along with the array A. And when computing the tree nodes of TQ, we retrieve the personalized Mason Bicliques under different thresholds, tau u and tau l. So the observation is that for the tree node n and its children n prime, we either have the n prime dot tau u equal to the size of the upper layer of C star plus 1, or we have this formula, and here C star is the personalized Mason Biclique of n. So, which means that from the top of the tree, following the path, we will have the parameter more and more straight, and the size of the Biclique is non-increasing. And here is an example to build the tree. So we first create the root node and using the parameter 1 and 1. And then we use the online approach to find the result CQ11. And we put the result into A and assign the pointer. And then we create the children node and process each children and store their personalized Mason Biclique into A. To further accelerate the index construction process, we propose a cost sharing across different search trees. And based on this lemma, this is because for 2 vertex, so if we compute a personalized Mason Biclique of U and the C star containing V, and C star can possibly also be the personalized Mason Biclique of V, and at least it will be a upper bound of V's result. And the second thing is because building the search tree is almost independent for each vertex, we can easily use the shared memory parallelization. And now is the experiments, and we evaluate our algorithms on 10 real-world datasets. Here is the result of the query performance. And OL and OL star are the online approaches, and RQ is the index-based approaches. We can see benefiting from the index, IQ significantly outperforms the online computation algorithms by up to 5 orders of magnitude. And the RQ algorithm can answer all the queries within milliseconds. So here we show the index time and the index size. We can see RC star can usually have a better query result compared with IC because RC star is deployed with the cost sharing strategy, and also the total size of the PMBC index is only 3.5 times to 6.1 times to the graph size, so it is very lightweight. And here is the conclusion of our work. This is the first work to study the personalized Mason Biclique search problem, and an index structure with bounded size is proposed. We also propose efficient and effective techniques for the index construction, and also we have extensive studies on the real graphs. That's all. Thank you for listening.